One. All right. Hi. Welcome back to Matthew 34. I'm your host, Steve Dragoo. I almost forgot what I say at the beginning of class. But we made it. Today, we've got the first round of section 15.7, which is triple integrals. And this is pretty much all we're doing for the next 2 weeks. Is triple integrals until the exam happens. So in true multivariable or Calc 3 fashion, we just keep doing Calc 1 topics until we do 3 of them at once for x and for y and for z. So a triple integral is like a double integral, but with one more. Hence triple instead of double. So what we're going to be doing then is just, instead of just a dx and a dy integral, we'll do a dx, a dy, and a dz integral. Meaning we need bounds for all three variables. So, just quick talking about what it is that these triple integrals actually solve. I think the easiest way to focus on a geometric understanding of a triple integral is to just follow the integral of the differential that we've been doing since back in Calc 1. Back in Calc 1, again, our differential is just dx. And if we only integrated dx, or maybe 1 times dx, we got the length of the integral. If we did a definite integral, that is. So let's just focus on definite integrals for the time being, meaning we have specific bounds we're going between. So in Calc 1, integrating dx, we got the length of an interval. Last week, and even on Monday, when we integrated dA, when we did the double integral of dA, we got the area of our region, because we were integrating over some 2D plane, some 2D area. So if we step that up to 3 integrals, a triple integral, so we take the triple integral of dV, our three-dimensional differential, we'll get the volume of whatever three-dimensional solid we're integrating over. So it's also worth focusing on the type of region that we integrate each time. Single integral, we integrate over an interval. For a double integral, we integrate over some two-dimensional region. And for a triple integral, we'll be integrating over a three-dimensional solid. So it'll have length and width and depth to it. So we'll have 3 dimensions that we integrate over. And again, if we just integrate dv, here written out as dz, dy, dx, we will just get the volume of that region. So this is kind of similar to how we were calculating volume using a double integral, where the volume was or we were getting the volume underneath some curve. So it's kind of like if we had already done our dz integral, and now we had that integrand that's showing up there. So if we actually had a function, we'd get the volume under that curve if we integrate it in, if we did a double integral of that surface. The analogy gets a lot harder to understand in a triple integral because we'd have to start thinking about a 4th dimension, and that's more complicated than we need to make them. So let's not try to think about it that way. Instead, we'll just consider finding volumes of 3-dimensional regions. Again, that'll just be integrating over dV. Or if we have a density function, where maybe density is our, or instead of density, let's go with mass is our 4th dimension. We can integrate the density over its volume to figure out the mass of an object. So maybe that's a better interpretation of what the triple integral of some function would be. So we can get mass out of density. And also we're gonna count b's, because we just really liked that example so well the last time we did it that we'll try it again. But practically speaking, here's what triple integral looks like. There are 3 of them. So we're just going to do an integral 3 times. Still going to fall back on our regular integration methods, though, where we just, integrate a function. Each time we do, we only consider The innermost differential. So in the order that it's written here, dz, dy, dx, though we can do any order, more on that on Friday. But we'll just start with dz, then we'll do dy, and then we'll do dx. Each time we go through it, we'll treat every other variable that isn't the one I'm interested in like it's constant, just like we did with partial derivatives, and just like we did with double integrals. So integrating xyz plus 1 dz gets me to xyz squared over 2 plus z. So wrote that integral over in the margin, but then plugged some numbers in, got another value. Then I've got negative 2xy plus 2 that I'm going to integrate with respect to y. So negative 2xy squared over 2 plus 2y. Plug in some more numbers, get another thing. By the time I'm done, I'm just integrating negative 5x plus 2. And then we're really just back to a Calc 1 integral. Negative 5x squared over 2 plus 2x. Plug some numbers in and end up with negative 52. Or at least that's what I saw. But again, the part that we should be focusing on here is that when we're doing these triple integrals, we're just going to do them one at a time and go through in order, just whatever our differential tells us to do. For now, at least, our differential is always going to tell us how we should do it, because we'll save the actually determining the order for the next class period. Make sure we get kind of a foundation first before we introduce the hard part. So, setting some stuff up. We're going to go straight into the generalized regions instead of only sticking over rectangular boxes. So when we got to general regions and we were doing double integrals, our first integral that we did, if I just go focus on that part for a second. The differential, again, we work our way inside out, and the inside tells us which integral to do first. So if we were doing dy first, we often found that we could have bounds that depended on x. And if we were doing dx first, we had bounds that could depend on y. Maybe I just go look at one of those examples real quick. I ought to have one here in this set. Yeah, I mean, this first example will do just fine. Right, we saw that if we were doing dy first, the y limits of integration, or the y bounds, could be a function that depended on x. But then by the time I got to the second integral, when I got to the x integral, I just had numbers there. Always constant values for the second integral we do in order. Same thing with this one right here. I did dx first, and I found that both of my limits for x, or both of my x bounds, could be a function that depended on y. But then by the time I got to the second integral, in this case y, it had to be done only in terms of constant numbers. Even when I switched the order, I still found that I needed to have the same constant numbers on the left side, on the second integral. But the first one could depend on the other variable, right? If I'm doing dy first this time, my function can depend on x, because I can still have an x by the time I'm done integrating y, because then I'll take care of that x when I get to the second integral in my iteration. And then again, over here on the right in the margins, we could find all the work to do there, but we're not really focusing on that today. We're doing, there we go. We're doing triple integrals, which means if we add one more to the list, ooh, what has happened here? I don't love that. Hold on one second. You guys aren't supposed to be able to move. There we go. That'll hopefully go better. Okay. All right, trying again. So we've got these various, try again. Getting into triple integrals. Now that I've caught myself one more time. We want to add a third integral to the mix. And the reason I went back to look at those double integrals was to talk about the dependency that these limits can have. Let's just focus on the right side, or the left side, for a second. I'm good at left and right, I promise. I've got my limits in order, A, B, and C. 1 on the bottom, 2 on the top. So that A matches up with the Z bounds, B is going to match up with the Y bounds, C matching up with the X bounds. Splash of color to kind of tie those concepts together. So if I'm doing DZ first, then its limits, its bounds, could depend on both Y and X. Because I still am going to do those integrals after dz. But then by the time I get to b, I'm effectively just going to be doing a double integral at that point. I'm doing dy first, so those limits can depend on x. And by the time I get to c, I should have only constant numbers for those bounds. The last integral we do should result in just a number if I'm doing a definite integral, which is what we'll be focusing on for the most part. And if I just slide over and look at another option where I just change up the order, again, using some color to tie into which bounds go with which variable, just look further to the right in the differential to see what those bounds can depend on. Anything that comes later, I can still have in my limits, or I can still have in my bounds. But after I do one particular variable, I shouldn't have a dependency on that variable anymore. So by the time I do my first integral, in this case is dy, I'll have no more dependency on the y variable because I'll have plugged stuff in for it. By the time I get to the second integral of 3, I'll only have x and z variables left. And by the time I get to the third integral, I'll only have the z variable left. And then I plug in numbers and I get a number as my solution. So that's my spiel. On to some other stuff. More specifically, you're getting an idea of how we go from the triple integral down to the double integral. Here was a sketch that I thought is kind of helpful for envisioning what we're going to do. Right, so that blue region, E, right, the blue guy there in the picture, is the solid region that I want to integrate over. And it looks like in this case, I'm going to be doing a dy integral first of my set. I can tell because I am projecting this thing along the y-axis into the xz plane. I'm projecting it along the axis to get rid of that variable, the variable I do first, which is going to be y. Project it into the xz plane, or the plane that does not contain the variable I just integrated over, and then that'll become my new integration space. So the triple integral, again, is going to be over some solid. But again, if I think of that triple integral as just an iteration of 3 single integrals, my second phase will be a double integral where I'm integrating over some area. And that'll be a projection of my solid into the plane containing the only variables that are left. So, with all that out of the way, let's just do examples until we run out of class time. So, some stuff that we might have looked at. When we did a double integral, again, we could figure out what our space looks like based on the bounds, or in this particular case, we're told the first quadrant and bounded by y equals 1 minus x. So that gives us a something. In particular, I think there's this line right here. It's y equals 1 minus x. And when I go to figure out the x bounds, I just need to find furthest left to furthest right. Or in other words, I could project that area down onto the x-axis and see that my x integral should be over 0 to 1. I know so because I've got this point up here, which is at 0, 1, and also this point at 1, 0. Right, just find the points of intersection of my line, 1 minus x, with both the y and x axes. And I want to kind of rely on that idea to think about what's going to be happening in 3 space. And we're going to use some computer-generated images for this first example, because it'll be a bit cleaner than me just trying to draw some stuff. But then by the time we get to the next one, we'll just be trying to draw them all out. So, similar enough looking set that we want to do here. We are going to integrate over the region in the first octant, being the octant where all three variables are positive. So x, y, and z are all greater than or equal to 0. And we've got the plane x plus y plus z equals 1, which looks an awful lot like the line y equals 1 minus x. So that's also the line x plus y equals 1, just adding in a z variable to it. So we want to consider a new integral. Come back here. I want a triple integral of x dv, but I want to spell out what dv ought to be. And I'm going to take it in the order dz, dy, dx. It's kind of our standard first approach. We'll again worry about picking a specific order a little later on. For now, I'm just going to say this is our order. So we're going to travel along z. And our goal here is to figure out what the bounds for z need to be. So if I'm traveling along z from bottom to top, so that'll be the order we want to go in, from bottom to top. I'm headed up from the bottom. That'll be my goal. And to figure out my bounds for z, or the limits of integration for z, I need to find my bottom surface, and I need to find my top surface. Again, top and bottom being relative to the z-axis. So I'm starting from the bottom, I'm working my way up. And in that case, if I work from bottom up, the first surface I'm going to run into is this triangle down in the xy plane. Let me try that one more time. I'm not super happy with. Yeah. All right. Good enough. Perfect's the enemy of good and all that. But I just can't help myself. Okay. So my first plane, my first surface is z equals 0. That's the first thing I run into if I come from the bottom and head up. Then if I keep going, straight up, and look for the next surface. All right, let's kind of move that so it's a little bit closer. I can see that the next surface that I run into, continuing to move straight up along the z-axis, is that triangular plane. This guy right here. Let's see if I can kind of sketch that out in a way that doesn't look too bad to be sketched over top of something else. All right, I'll hit that triangular plane second. The one that's that sloping face that we're looking right at. And that thing is, it is the plane of x plus y plus z equals 1. Plus z equals 1. Keeps. Whatever. We're gonna let it go. All right, where I got that plane from this equation right up here. So second surface I hit is that plane, meaning I probably have some limits I can set up for my z integral. So my integral right now is x, because that's the thing that I'm integrating first, dz dy dx, where my z bounds start at 0, and then they go to 1 minus x minus y. Because I got that from taking the plane and solving it for z. Just like we looked at in double integrals, the limits of integration for whatever variable ought to take the form of blank equals some function, where that blank is whatever variable I'm going to be integrating over. In this case, they should all take the form z equals something. So z equals 0 and z equals 1 minus x minus y. So with that part done, now we just need to get the remaining bounds. And the goal with that is going to be to project this surface, or project this solid, I should say, down into the plane that only contains the variables that are left over. I did z first, so I'm projecting down into the xy plane. So that's the space where my remaining variables exist. They're in the xy plane now, so I've already integrated over z. So if you look at that highlighted blue triangle, same blue triangle we highlighted a second ago, but I'm just going to rotate that and put it into a 2D plane with the usual x to the left and right, y to the up and down, and start looking at limits on that space, or on that area, that region. So I've got a few bounds that I need to come look at. One is this line right here. And then the other two are going to be the axes. But let's focus on that orange line that I've just drawn in. That thing has the equation. Hey, stop it. Y equals 1 minus x, or x equals 1 minus y. Couple of ways I could go about formally defining that line. I've got my 2 points, 0, 1, and 1, 0. I can just find the equation of the line that connects the two. Or I had the equation of the plane, which at a time was x plus y plus z equals 1. But I've projected this thing into the xy plane, where z is 0. So projecting that thing down into the xy plane, again, z is 0 there. I get the equation x plus y equals 1, which I could then solve either for y equals 1 minus x or x equals 1 minus y. Just depends on the order that I want to go in. I think we decided to go y second and then x third. So we'll stick with y equals 1 minus x. But then I'll also want this line right here, y equals 0. And my left boundary, it's the y-axis, x equals 0. So with all of that together, let's figure out what this thing should be. Let me grab the integral that we were working on. And come down and repaste it right here. And it's a little too big for this space. So shrink it down just a little bit. Add in our final limits. So we're doing y second, which means I need my y boundaries. Now from top, or from bottom to top, it's 0 along the bottom because I have y equals 0, and 1 minus x on top. And then my x limits are 0 to 1. And then just like that, I've got all the limits I need to go integrate this thing. So there's the new fancy skill that we got to get used to in triple integrals. The last step is just integrating that thing. And that falls back on methods that we already know and love. So let's just give it a shot. See how well this goes. Copy that. Paste it right here. I can probably make it a little bigger for this part. Thanks for all the color we added in earlier. So if I want to integrate this thing, I'm doing Z first. So I'll just come highlight those parts. Do a Z integral first. So this thing looks like what is now going to be a double integral of x times 1 minus x minus y minus 0 dy dx. And then I can probably just distribute that x through this part, right? So I'll call that. Yeah, let me just undo that first. This will be x minus x squared minus xy. Right? After I distribute the thing. Just clear that out of the way, move that thing in. And we're still going from 0. Yeah, let's actually fill this in yellow. 0 to 1 minus x. With x still going from 0 to 1. And now it's time for a y integral. Let's try that part next. So if I'm going to do that, I'll still have one integral left. On the one hand, x minus x squared, neither of those depend on y. So I'm just going to call that x times 1 minus x times y after I integrate it. Minus xy, its integral is going to be 1 over 2x y squared. Still throwing a dx kind of floating out over there. And evaluate that y integral. L, if I just plug in 1 minus x for y, I'll get that. Plugging in 0 for y, I'm just going to get 0, so I only need to worry about the upper bound for now. So this thing is going to look like 1 minus x squared. If I can just slide that to the left a little bit, because I left not quite enough space to write in another 1 minus x right here. X still from 0 to 1. Then it looks like this thing actually simplifies pretty nicely, which is fortunate, because otherwise this looked like it might be kind of rough. But this thing is going to simplify to 1/2 of x times 1 minus x squared dx, still from 0 to 1. Okay, I'm almost out of space. So let me add in one more step right here. I can pull the 1/2 out, still iterating from 0 to 1, foiling this thing. 1 minus 2x plus x squared becomes x minus 2x squared plus x cubed dx. And then that thing is fairly integrable. So still 1/2, but now multiplied by, let's see, this will be 1 over x squared over 2 is just 1 over 2 if I plug in 1, minus 2/3 of 1 cubed. Let's call it a 1 squared right there. 2/3 of 1 cubed plus 1 to the 4th power over 4 minus everything else is 0. And now just finish evaluating this thing. What are we going to have? This looks like it'll be 1 over 4 minus 1 over 3 plus 1 over 8. If I multiply that 1/2 through. Cool. And then if I really wanted to combine some fractions, I could do that, but let's not and say we did. Yeah. So again, I think that the new stuff is the real meat on the triple integrals set is just setting these things up, integrating them, while tedious should just look like methods that we have already used before. I hope. All right, let's try something again. Evaluate the following triple integral. 2y is our integrand, and our solid is bounded by 0 and 1 for x, 0 and 3x for y, and x minus 8y and 4y plus x for z. So if I just come through and take a look at what variables I see x in the y integrand, or in the y bounds. I see both x and y in the z bounds. And then I don't see anything but constants in the x bound. Meaning I should come over here and do z first. I'll do y second, and then I'll do x third. Just based on the bounds that I have for those variables. Remember that as I move through my differentials, as I move through my iterated integrals, each integral on down can no longer depend on any of the variables that came before it. So since z depends on both x and y, it's got to come first. Or rather, it's got to come before x and y. Y depends on x, so it's got to come before x. X only depends on constant values, so it can go wherever, which means it'll go last. But let's go set this thing up. We have another triple integral. I probably wrote that too big. The real trick with triple integrals is trying to get 3 integral signs that all look the same. It's harder than it might seem. You'll see soon enough. So I'm still integrating dy, or 2y rather, and I decided I'm going to do dz first. So I can go put its limits in. Looks like x minus 8y on the bottom and 4y plus x on the top. Then y was 0 to 3x, and x is 0 to 1. So let's put a dy and a dx in right there. All right, and then I just go integrate this thing. In particular, if I have to integrate 2y dz, that integral is going to be 2y z. And then evaluate between my two bounds. So this is going to be 2y times, well, 4y plus x, 4y plus x minus x plus 8y Which after simplifying all of that mess, I think I get 12y minus 0x. Which maybe you could have seen that from the bounds right away. But so we don't need this 0x anymore. It can be gone. Simplifying that whole mess to just replace it with 12y. And then I'm integrating dy dx. Y still from 0 to 3x. 3x. X still from 0 to 1. That has not changed. So this thing looks like the following. 12y times 2y is 24y squared dy dx. And we've got y next on the list. Okay, there's still enough space. So if I integrate that thing, what are we gonna get? Well, 24y squared is going to integrate to 8y cubed. 8y cubed. Or 24y cubed over 3. 24y cubed over 3. Which is going to look like, hey, come back here. 8 times 3x to the power of 3 dx, still integrating from 0 to 1. Which, if I factor an 8 out, I am looking at the integral from 0 to 1 of 27x cubed dx. Well, now I'm finally going to be evaluating between 0 and 1. Which, that thing, of course, will integrate to x to the 4th over 4. I already conveniently have an 8 there. So this will be 2 times 27 times 1 to the 4th power minus 0, which is 54. Hopefully that's the answer we all got, right? Zoom out for a second to kind of put all of this on screen. So you can still kind of see that stuff at the top. Hi there. I'm paying attention. No, awesome. I love that for me. Never mind was the question, if you're wondering on the video. All right, let's go try another one. Yeah. So triple integrals, I think, aren't too bad if you're just told what all of your bounds are. Particularly if you just got a rectangular box, you can go in whatever order you want. Just you set it up and you do it. We had an example where we were given a diagram, told what order to go in, or at least I told you we were going to do dz, dy, dx. And then what did we do next? The next one, we were given bounds directly, and there was a natural order that already made sense. Those ones are, I mean, like medium hard, but they're not nearly as bad as this one. So let's brace ourselves for a second. And I don't know, prepare for glory. This time we've just got a few equations and told there's some solid that's bounded by those equations. Figure it out from there. So, step 1, sketch this region and set up a triple integral that calculates its volume. We're given z equals 4 minus x squared, x equals y squared, and we're in the first octant. which means we also have x equals 0, y equals 0, and z equals 0 as bounds. Those just being the x, y, y, z, and zx planes. Not necessarily in that order, though, but that's fine. So let's try to sketch this thing. It's going to be real fun, I promise. So I need a coordinate space. So a vertical line for z. How about a line at an angle for x? And let's also keep y at an angle here as well. I think it'll be a little easier to see the shape that we're trying to sketch. Let's try that. All right, so this will be z, this will be x, and that'll be y. Let's start trying to sketch this shape. So my first equation that I'm going to try to get down here. Z equals 4 minus x squared. Notice conveniently that both of these shapes are cylinders from the mathematical sense. Don't forget your quadratic surfaces and all that stuff that we did way back in like the second week of the course. It's that lesson keeps coming back. So we have to sketch out these two cylinders. I think it'll probably be helpful to just start by sketching what they look like in their planes. So if z is equal to 4 minus x squared, this is a parabola starting at 4 on the z-axis and opening down in the x direction. So if z equals 4 is maybe this point right there, I want a parabola that opens down and hits the x-axis. Something like that. Get rid of that for now. And then I could sketch out some shapes of what that thing will look like, which I will do in a moment. But I also want to come get my other base shape down. X equals y squared. So that is another parabola. This one will be in the xy plane. And I want this thing to open in the x direction, since x is my linear variable. So if I just sketch out that shape, again, another parabola, should look something like this. This blue shape, this blue guy down here, that's x equals y squared. My green shape, z equals 4 minus x squared. So I have those shapes that show up, and now I just want to sketch out what they look like a little later on. So I should have, again, these things are cylinders. So they'll be unchanging along the axis of the variable that we don't have in the equation. Meaning, if I'm going to go sketch out z equals 4 minus x squared, it'll look, basically it'll have these traces, right? The traces are what we call them. The parallel lines that all run in a direction. These traces should all run parallel to the y-axis because it's not present in that equation. And I can just get the same parabolic shape connecting from one line to the other. But that shape's going to be in front, so I'm going to draw the one in back first. If I just look at the way that I want the traces for the blue parabola to go, let's see, how high up should that go? I don't know. Let's draw it all the way up here for now. I should have some parabolic shapes that go from the blue line back to the z-axis. So something kind of like this. And maybe another one there. All right, so we sort of got that parabolic shape in the background. See, can I, arrange, bring to the front. Put the green line in front of the blue lines. Because then I want to do the same thing with these green parabolas. They should all connect up like this. The last one kind of going over here. And maybe sort of roughly we can start to see our figure take shape. I have these two intersecting shapes where I've got a blue parabolic cylinder in the back, and I've got a green parabolic cylinder in the front. And there's an interesting sort of intersection between them, kind of near where that vertical blue line I drew was. So let's take this shape now that I've drawn it out. Now that we've drawn it out, we're in this together after all. Hey, don't be like that. And start erasing some pieces to see if we can figure out what shape we're actually supposed to be seeing here. So if I were to get rid of just some of this shape, this part out here, we don't have an intersection at. We don't need this tall blue line right there. And in fact, we probably need to just start erasing all the way out like here. Because to get the shape along where they intersect, because of the way that they come together, I think that we'll have a parabolic shape along that curve of intersection that starts down here at the intersection point in the XY plane. Maybe I should draw this in a new color. Intersects down here in the XY plane, kind of follows that original blue parabolic curve I drew in, but it needs to work its way all the way up to come to that point of intersection along the z-axis as well. Again, I think our shape kind of looks like this. Keep darkening that line in because I don't want to see the parts that are behind it. Sort of the 3D shape, if you can kind of visualize that a bit. It's got some other pieces to it, like this face here in the back along the XZ plane. And also we've got a floor to this shape along here in the XY plane. That is for sure the hardest part of this problem, is trying to visualize that shape. Because then I need to turn this thing into a triple integral. And I got to pick an order. For now, let's see. I think Z makes sense to do first. So if I look at Z and come from the bottom, I come from the bottom to do Z. From the bottom to the top, it's got a floor at Z equals 0. That's the part I would run into first. And the part I'll run into second is the green shape, the green part, 4 minus x squared. If I'm going from top to bottom, again, I'm doing dz first. Then, because I don't want to deal with square roots, I'm going to try dx second. And this one's a little bit odd because I need to come from the back and go forward. So something like this. And if I come from the back of this shape along or something parallel to the x-axis, the first shape I'm going to run into is the blue one, y squared. Then I'll run into the green line that's down there. I'll come figure that out in a second. And then for the y bounds, I also know I've got 0 first, but I'm going to need that orange intersection point. So let's go start figuring out what those pieces are. I need this line right here. Let's try that again. This line along the front face. Right? So the intersection of the green cylinder into the XY plane, or in particular, if I just knew what that intersection point there was, I think I'd be okay. So if I'm looking for that purple line where the green shape hits the XY plane, that's going to be where z is equal to 0, meaning x squared is equal to 4, so x is 2. Right, you can just check real quick. If x is 2, 4 minus 4 is 0. So that's my line down there. And if x is 2, over here, trying to find the y value that matches that point. If x is 2, y is the square root of 2. And z is just 0. So to finish out what this graph should have looked like, that thing is 2. And this point over here is the square root of 2. Oh, and don't forget our dy. We gotta write that in at the end. I must certainly be over on time, right? Oh yeah, I am. Cool. So that's setting that thing up. And then we'll just integrate it. So again, I know I'm out of time. So if you've got somewhere else to be, you can be dismissed and you can run off and go to that next class. The last integral should only take me about 2 minutes. So I'm going to finish it up here in class. So let's go do that. So part B asks us for, there are B's inside this solid with a B density function of xy. So let's just take our integral over here. Oop. And come integrate it. So again, this was my volume. I just need to integrate my B density function, which was xy. And just clean it up a little bit, turn everything back to black. It's a little larger than I wanted it to be. Shrink it slightly. All right, and hey, cut that out. And we're gonna do z first. All right, so trying to integrate this thing. I have a double integral of x, y, 4 minus x squared, dx dy, still from y squared to 2, and from 0 to square root 2. Which if I go, oh yeah, we are like so out of space to get all this done. Another double integral. This looks like 4xy minus 4x cubed y. We go from y squared to 2 and from 0 to root 2 dx dy, and try and integrate that thing. What do we get next? This looks like the double integral of, oh yeah, this is going to be messy. 4y times 2 squared is 4. Oh, and also it's not 4y. It'll be 4 over 2. So let's call that 2y. 2 squared is 4 minus y squared. Squared is y to the 4th. Minus. I'm not supposed to have that 4 there, am I? Minus 1/4 y. Now I have x to the 4th power. So 4 to the 4th is 16 minus y to to the y squared to the fourth is y to the eighth. Yeah, this thing is becoming a mess real fast. We still have a dy here. Nope, we have a dy here. There it is. From 0 to the square root of 2. Simplify this thing. What do we have? 8y minus y to the 2y to the fifth minus 4y plus 1/4 y to the ninth. Yeah, that looks about right, doesn't it? Yeah. All right, this is dy. I'm still going from 0 to the square root of 2, and I'll integrate this mess. Maybe I'll start by saying I can get rid of this minus 4y and that 8y to just call it 4y minus the rest. All right, and integrate this thing. So this will be 2 times the square root of 2 squared, which is just 2, minus 2/6 times the square root of 2 to the 6th power is going to be 2 cubed, which is 8, plus, okay, let's see, this is 1/4/10, so 1/40th of the square root of 2 to the 10th power, which is 2 to the 5th, which is 32, I think. And then this all works out to a number, doesn't it? Let's just say it's about 2 B's. I don't know. I've never been good with numbers anyway. Let's call it there. Again, the integration can get tedious at times, but it's really not the hard part. The hard part is, of course, figuring out what that shape looks like. And of course, it's a B carrier, so it's got to look weird. Anyway, that's enough from me. Okay, bye. Bye, 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 bye.